People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story. Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencastr.com/pricing and use my code BREAKINGMATH, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your...
Michael Brooks is a science writer who specializes in making difficult concepts easier to grasp. In his latest book, Brooke goes through several mathematical concepts and discusses their motivation, history, and discovery. So how do stories make it easier to learn? What are some of the challenges associated with conveying difficult concepts to the general public? And who historically has been a mathematician? All this and more on this episode of Breaking Math. Episode 69, an interview with author Michael Brooks. I'm Sophia.
And I'm Gabriel.
And I'm Meryl.
And you're listening to Breaking Math. With us, we have on Michael Brooks.
Hi.
Welcome to the podcast, Michael.
Thank you.
Yeah, thank you so much for joining us, sir. I see this is your second book. Real quick, can you tell us a little bit about your first book? And then the next question will be, tell us about what motivated you for your second book.
Okay. Well, actually, I mean, there's been quite a few books. So there's been sort of 4 or 5. There was a big success with my first book, which was 13 Things That Don't Make Sense. Which was probably like a decade ago now, and that was a book about scientific anomalies. And since then, I've written books about kind of what the next discoveries might be, and about how science actually works.
Oh, and just to clarify, by scientific anomalies, do you mean like quasars and stuff?
I mean things like dark energy and dark matter, where 96% of the universe seems to be missing, and scientists can't understand what it is. So it's about things that scientists are working on but haven't really yet figured out. And kind of, it was motivated by the Isaac Asimov quote, where he says, the most important thing to hear in science is not eureka, but that's funny. And it's just kind of like, that those things are the things where you get breakthrough. So, but this book was inspired really by kind of going through the decades of, being a science writer. And, I trained as a physicist. I did a PhD in quantum physics. And I just kind of, had this growing realization that behind everything there was sitting this bedrock of mathematics, right? That nobody really kind of engages with properly in society, as far as I can understand. You kind of leave it for other people to do in a lot of cases, unless you're like actually working in the field or doing something technical. But people didn't understand just how important mathematics was, not just for doing like technical stuff in the 21st century, but actually it was important right from the start of kind of humanity starting to settle into agriculture and building cities and finding ways to create great architecture and art. So it was kind of an exploration of all that stuff that maths has actually been doing for us for millennia, rather than just thinking about, it's maths that makes Google work.
Nice. And I really like the story approach that you took to everything. I was talking to Gabriel right before we did the podcast, and I was telling him how when I'm having trouble with like a math or science concept, sometimes I look at the history section on Wikipedia and kind of see the motivation for the problem, where this came from. Was it a puzzle? Was it a real problem being solved? And your chapter on Napier and logarithms kind of, I think, shows that process beautifully. But let me ask you a question just to get this not necessarily started, but to keep things going. How do stories make it easier to learn?
Oh, I think because it just engages all of us, all of our humanity, if you like. Because I think, we're much more motivated. As you say, you can kind of get your brain switched on much more if you understand why you're learning something and where it came from and what it might be useful for. So if I tell stories about, where this math came from, automatically you're like, oh, okay, I can see what problem they were trying to solve, or I can see there was a person behind this who, and when we see human beings doing stuff, it's much more interesting and engaging than when we just see, equations on a board. And I think this sort of goes down to, how we learn in school and particularly how we learn mathematics. It tends to be, here's how to solve this problem. Here's how to pass this exam. Here's how to get, yourself from A to B in terms of learning math and progressing to the next level, without ever really understanding where these things came from and why you're learning them. And it's interesting because with a lot of math, I think you can say, well, you don't need to learn it. Like, I would say like 80% of people are never going to use a quadratic equation in their, once they've left school, kind of thing. But actually to learn that quadratic equations and their solutions were kind of part of Babylonian culture, to like help them collect taxes and understand how to kind of run a civilization, because you need the money and you need to tax people, and how do you do that fairly? And it comes down to working out the areas of fields and things like that. And to me, that sort of brings the whole idea of, algebra to life, much more than just, here's the equation, here's how to solve it, and then move on to the next one.
I really, really appreciate you saying that, and about that touches on why math can be frustrating for a lot of people, or why a lot of folks might not get it. I found that in my degree, my undergrad in electrical engineering, there were times where I was doing a derivative of e to the x so many times that I didn't even think about it. I didn't even appreciate it. I just knew you do this to this symbol and you get this, and then I move on because the test is too big and I can't appreciate what e to the x is and and why is a derivative of e to the x just e to the x. I don't know, but I just do it. I just do it, Don't ask questions. So it's the opportunity to actually read a book like yours or similar books and to see the bigger picture of what it actually means. I think that is so necessary for people to really understand the beauty of mathematics, because they're missing so much. So I just think that's awesome. One of the questions I had for you, well, it's kind of a two-parter here. I have a rough outline of questions I made. I want to ask you about putting together this book. One of the two questions is, what was the hardest concept to research and put into layman's terms? But then a dovetail question is, tell us about the order of your book, and I mean, obviously it's chronological, but like the structure of your book. Like, what did you learn about yourself and your understanding of math as you put the book together?
So let me start at the beginning. So the hardest thing that I think I had to come to terms with, weirdly, was probably not like the hardest mathematical thing. But I found when I was trying to explain how logarithms work and where they came from, and and I was looking at the work of John Napier and saying, oh, this guy like did 10 million entries, and it took him 20 years to create the first sort of book of log tables, and working out exactly what he did and how he kind of calculated these things, like I sort of go into it in the book, like beads moving along a wire, and you calculate the angle and the sine of the angle, and then that sort of gives you the logarithm is the length that's left on the top of here, and then you progress to the next thing and the next thing. It was just one of those things where I just got this terrible mental block, and I was just like, I can't get my head around what he did, and sort of feeling like, this is ridiculous. This was like the 17th century. The guy was, it wasn't complicated maths particularly, but there was something in me that was just like, oh, this is hard. And I think that's probably true of everything for everybody. Like everybody has these things that they find quite easy to visualize and conceptualize, and other people just sort of, find them hard. I didn't find derivatives and calculus that hard to get my head around. I think information theory, which is my last chapter, is sort of much more conceptually difficult in some ways. But as far as the structure of the book goes, it just made sense to me to start with arithmetic, right? Because it's, that's the first thing we did, and it's kind of the basis of everything. And once you understand, what numbers are and what they're not as well, they're not these real things. They're these concepts and these things that act as tools, for us to grab and then sort of, do trade or, keep accounts and do that kind of thing. Then you start to see how from there you go to measuring, like, oh, well, how long is this length of rope or something like that? And then you get into geometry from that and the shapes. And so the first two chapters are arithmetic and geometry. And then, we're sort of getting into algebra and calculus, which are the kind of next things to really come along. So a lot of it is kind of logically, kind of chronological, I guess. But I did then want to sort of get into things like imaginary numbers. I mean, as an engineer, you'll appreciate imaginary numbers, are just the most fantastic things and not at all imaginary, and or no more imaginary than other numbers anyway. And so incredibly sort of useful and literally built Silicon Valley, literally built electronics and the electrical sort of age of the early 20th century. Everything was sort of predicated on us being able to manipulate these imaginary numbers. And I just kind of felt like, they were so important and so under appreciated in the world that they kind of get, it was like, okay, they get their own chapter, and that's just going to be how it is. It's my book. I do it how I want. And then statistics, I felt, was another thing that like didn't necessarily fit chronologically, but I think it's a really important thing. And again, certainly where I am in the UK, we don't really teach it in schools. People don't really get to it until they're doing a technical subject at university for the most part. And then for most people, that's not ever going to happen, right? So and statistics is so important. If you get a grasp of statistics, and you can navigate the world so much better than if you can't. So I felt like that was a really important mathematical breakthrough in terms of our civilization and the way the world works for us. Is you've got to kind of understand where statistics come from, especially in an age of like of compressed data that's streaming through the internet, and everything is done statistically. And then finally, the final chapter, which is about information. It's kind of the work of one guy, Claude Shannon, and it comes sort of through. Really, the sort of middle third of the 20th century, is the information age where everything sort of gets established, and again, that's a thing that people live with every day. They're living the consequences of Claude Shannon's work, but nobody really, outside of the subject, really knows that much about him. His name isn't well known. He's not Einstein. So for me, it was such an important thing to be able to say, look, this is the age you're living in. It's a mathematical age, and it comes from this part of maths called information theory, which has set up so much in our daily lives. And so again, I just thought, this is an important thing to include if we're talking about how we build civilization.
Oh yeah, that makes total sense. And it seems like your focus on the whole book was civilization. I mean, you've mentioned that several times. Stories making it easier for humans to grasp concepts. You touched on that earlier. I wanted to ask you, after doing research for this book, what can you conclude about historically who was a mathematician?
Oh,
Like, it seems like a lot of time, and this is something I always noticed in school, was that you have these people, it's like they seem to have immense resources at their disposal. Do you have any comment on that?
well, I think, in different times, before we had, grand universities and academia, you didn't really have to engage with numbers in the same way, perhaps, in daily life. I mean, if you're trading in a market, you're doing arithmetic, you're doing basic stuff. And there's relatively few people who are doing like innovation, like, creating new maths and being a mathematician. And, so you have people like Cardano in the 16th century who is, coming up with new solutions for algebraic equations, but he's working as a teacher at a university. John Napier is a Scottish aristocrat nobleman. He's got family money, so a lot of the innovation I think comes from people who have the leisure time to be spending doing that kind of thing. But in everyday life, people could do arithmetic. There's an interesting thing around when Cardano was doing he wanted to write this book on algebra, and he gets into this massive fight, feud with the guy called Niccolo Tartaglia over him publishing, what was supposed to be a secret result. And at that time, mathematicians were looking for jobs and looking for employment and looking for people who would pay them to do the maths, and it was important to them to be the best sort of around. And they would effectively do public duels. They would do mathematical competitions in the streets. So this is in like Renaissance Italy, and people would watch these competitions and see which mathematician was solving this and which one couldn't do that. And so I think there may well have been a situation where in certain regions of the world, you had people who were just running market stalls or selling cloth from a shop or something, but actually had an appreciation of maths. And at the time, people were actually circulating pamphlets about what these disputes were about and about algebra and how algebra works and why Tartaglia is saying this and why Cardano is doing that and what this all comes from. So I think you had specialized mathematicians who were pretty few and far between, but actually you also had, I think, people were generally sort of cognizant of numbers and how numbers work, and the fact that mathematics was generally kind of venerated and important.
That's fascinating. Also, I want to like go into the past and see these. I'm just imagining two mathematicians in a circle, and everybody's like throwing dice, trading money, like betting on the mathematician.
I mean, the funny thing, one of the funny things about Cardano is that he invented probability theory. He was the first person to write out probability theory, and he did it because he had a gambling problem. So he kind of was losing money, and sort of worked out how he should bet when he was was placing these bets. He kind of worked out if there's this number of cards in a deck, and I need one of 6 of these, then these are the odds of me working this out. So it was a very practical discipline really in those days.
I like how it's practical, but he's still betting things. So isn't that essentially a martingale?
I mean, he was kind of the only guy in the whole world who knew how this whole thing worked, and he was still losing money. So it was amazing.
It reminds me of those people who work on slot machines who still use them.
Oh my gosh, that's wild, isn't that? That is so. Yeah,
wild. They'll go on their lunch break and after manipulating statistic and manipulate themselves.
Yeah, I know. Yeah, so the human brain itself is so prone to error. That's crazy.
That's so
crazy.
True.
So I want to know 2 questions. Who's your favorite mathematician in the book, and who's the most eclectic to you? I mean, I know Napier is pretty eclectic. I mean, we talked a little bit about one of our episodes, the story about one of his servants was stealing stuff, so they made everyone touch a black rooster in a dark room, and the person without soot on their hands that was on the rooster was the person who was stealing. And just like he's a fascinating character. But who are your favorite characters in mathematics?
Well, so I guess Cardano has to be up there. I mean, I one of my other books was about Cardano and about the role that he played in sort of establishing the foundations for quantum theory, which is kind of my discipline. So I wrote that book about him, and so I guess I've always been fascinated by him. But I think also his arch rival, his nemesis, Niccolo Tartaglia, really impressed me the more I dug into his life, because he had this thing where he was using maths and developing maths And he had this appalling backstory where he was maimed as a child by some French soldiers, and he could hardly talk as a child, and which is why he was called Tartaglia, which means the stammerer, right? So he couldn't really talk properly because he got maimed by this Frenchman's sword as a child, and he just pulled himself up, really educated himself. He had about 6 days of schooling, and then stole the teacher's maths book or textbook, and like kind of took off with it, and so he could teach himself the rest of it because he couldn't afford any more school. And he actually became a really, really great scholar. And not only that, but he was a pretty interesting human being in that he developed the science of artillery. So he had invented the mathematics of how to aim a cannon. So he was the first person to kind of write down the kind of formulas for how to aim a cannon if you want it. If you have it at a certain angle with the barrel, you'll get this kind of distance.
And that's pre-Newton, right?
Yeah, very much so. And he just tore up all his notes because he realized this was going to be used for killing people. And he didn't want anything to do with it. So he actually burned his manuscripts and said, I'm not having anything to do with this. This is a terrible thing because I've realized what I've done is just facilitate humans murdering each other. And then eventually he was in Renaissance Italy. There were the Crusades going on. There was a kind of Islamic insurgents into Europe, and they were fighting. There was lots of fighting between the Catholic Church and the Islamic forces. And in the end, he felt like, God wants me to kind of do this work. So he, for religious reasons, he kind of redid all his calculations and wrote them out and showed the generals how to aim their artillery. But he had this real crisis of conscience, which I really like. And that goes on. That's a very human thing. Like we still have that now. The scientists who work on the atomic bomb, they were really sort of torn for the most part about what they were doing and whether it was a good thing. And I think it kind of shows how intimate the interaction between mathematics and humanity and civilization really is.
Wow. The way you said that, I really, really firmly appreciate the interweaving, like two strands of DNA between the humanity and the stories and the geopolitical conflicts and mathematics.
Yeah.
So the whole story element just makes it really, really rich. So, wow, that's really cool. I have a whole bunch of questions that have come up, but I would like to give the floor to Meryl. How are you doing, Meryl?
Doing well. And I wanted to say that one thing that's been mentioned as well, I am fascinated by the story of one particular chapter in this book. Also having an engineering background, I think we all have at least a little bit of engineer in us. One thing that always, appealed to me was imaginary numbers in particular. And so that's one thing I enjoyed was how you started with the story of Fender and how amplifiers as we know them would just not exist because without imaginary numbers.
Yeah, it's an incredible thing to think that, it was really hard to produce electrical circuits because, if you're an electrical engineer today, you know exactly how to design any circuit that you want to do. But it's sort of fairly straightforward because you use imaginary numbers as a J symbol in all these equations.
Mm-hmm.
And when we were looking to kind of first sort of roll out electricity into cities, make it something where, people just had it in their homes and their offices and factories and things, everyone was working in terms of sines and cosines and these like ridiculously cumbersome calculations for, what a circuit would do and how to predict, and how to design the circuit that you want. And it was just sort of impossible. And then along comes Charles Steinmetz in, I think it was 1893 at the Chicago World Fair, and just sort of says, hey guys, you can like get rid of the whole of the sine and cosine problem with your alternating current if you just use imaginary numbers, and kind of just completely revolutionizes the way that engineers can work, which brings you, radio, circuits and it just becomes easy to kind of produce these manuals for how to produce radio circuits and how to produce all the electronic circuits. So it just becomes like common, like to be able to manipulate electric circuits. And Leo Fender was working as a radio repair guy, and just sort of then branched out into kind of PA systems for events, and then into amplifiers, and then we got the Fender electric guitar amp, and it's kind of the rest is history. And it's all sort of stems from that sort of twist where you bring imaginary numbers into the game, and suddenly everything's possible.
Right, because instead of your regular idea of voltage or current, now we have phasers, which phasers with an O, not an E. It's not the Star Trek kind. But also things like, we don't think as much in terms of capacitance or inductance or resistance. Now we have impedance, which is complex and accounts for all of those things.
Yeah.
And then that can tell us, now we have magnitude and phase all wrapped into one, and the more you learn about how complex numbers as a whole work, well, you're thinking of it as a vector with a magnitude and an angle. Well, all these different things are possible now, and I still, to this day, the way you keep seeing those interrelations, the more different things you work with, and it just all keeps coming back to that.
Yeah. And I love the fact that these complex numbers are just, they are a mix of what we call real and what we call imaginary numbers. But actually, they're just two sets of numbers that allow us to work in these, in these kind of multifaceted ways. So I think when people first come across them, imaginary numbers seem absolutely terrifying, but they're no different to normal numbers, and it's just this whole system of complex numbers allows you to just do something that's just, kind of out of this world.
But that's the amazing thing, though, is it's also very in this world. And I think it was, when I took a class in undergrad on signal processing that it really hit me like a brick that complex numbers describe something, they quantify something, that they're tangible, that, you don't just have, because if you start thinking in frequency, now you have your frequencies, but you also have the phase. And now we can account for both of those because phase is just an angle shift. And that's mind-blowing.
Yeah. And, for me, you can't have quantum physics without imaginary numbers, without complex numbers. It just doesn't work. You literally, the theory isn't there without that.
Right. And that's something I'm a little less well-versed in, if you would like to go into more detail on that.
Well, I mean, I'll just a little bit. Basically, because we describe things using the Schrödinger wave equation, and it's exactly the same as in signal processing, electrical engineering. You've basically got a wave that's kind of that's progressing, and so anything that you describe as a wave, you use imaginary numbers. So whether it's signal processing in electronics or in the wave function of a quantum object like a proton or a photon of light or whatever, then you use exactly this, the phase and the magnitude, in order to fully describe this thing. And it's an incredibly successful thing where you can build a theory that involves a wave equation with complex numbers in it, and it describes the most fundamental entities in the universe.
I wanted to bring up too that wasn't it Descartes? I think it was Descartes who didn't believe in negative numbers completely. So learning that kind of made me realize, oh wait, an imaginary number is a complex number is not a pair of real numbers any more than a negative number is a pair of real numbers. Like you could do -3 is 5 minus 8 or whatever, and they're both positive. But
I think our concept of numbers is something we take so for granted now, right? Because it's one of the first things we learn when we're babies. Our parents will sort of teach us these number rhymes, and we'll learn to count, and we'll start to associate, two objects with the number 2. And so we think of numbers as, they're like our companions through life. And then, but those are all like normal counting numbers effectively, aren't they? So as a child, you learn to count, up to, and you keep going and you keep going, and you think, oh, I can count up to 10,000. And then your friend says, I can do 10,001. And it's, it's like this goes on forever. And that's all great. But actually, we're in a position where, then suddenly sometimes there's just an abrupt shift. So people bring in things like, somebody starts using negative numbers and saying, okay, well, we can have these positive numbers, and we've had them all of human history. And then just literally a few hundred years ago, really, people started saying, okay, but what about these negative numbers? And it was much earlier in China and India, I have to say, than it was in the West. And people...
Yeah, they used red ink, right?
Sorry?
For negative. I just wanted to point out that our modern accounting practice of using red to do negative numbers actually comes from China, but I didn't mean to interrupt.
It comes from Chinese who used maths for accounting and business and used negative numbers to symbolize debt. And so it just became really easy for them to kind of do more complex accounting because they were basically using debt, and in India too, and using these concepts just, to do business. But in the West, we kind of had this conceptual, brick wall where it's like, you can't have this. Which is why you get Descartes saying, people say that, you can take away 8 from 4, but you can't. That's ridiculous. And sort of it amuses me that, I mean, Descartes was this incredible luminary in mathematics, but now you would have elementary school children who would teach him a thing or two.
Yeah, that's incredible. That's incredible. I have a quick question for you. This is a very, very exciting time. I say quick question. I'm a liar. This is a very, very exciting time in science communications. And I know that you had mentioned that you have a PhD in quantum physics. This question is inspired by a couple other science communicators on YouTube. I don't know if you have any favorite YouTube science communicators. Do you have any?
My favorite,
I shouldn't say favorite.
Yeah,
admired ones.
I really admire. There's a woman called Sabine Hossenfelder who does.
I have her on my phone right now. That's her. Yeah. That's her. Yes,
she's great. She's just great, and I do know her. We've met a couple of times. In the times when back when we were allowed to meet. But she's a German scientist, and I just think she's incredibly smart and funny, and also brave. I think she's quite a courageous communicator.
I think she is. Now, here is why I wanted to bring up her, and her channel is called Science Without the Gobbledygook.
Yeah.
There is another YouTube channel that is done by PBS. It's called PBS Spacetime by Dr. Matt Dowd, I believe is his name.
Right.
Recently, Sabine released a video critiquing one of his videos, and he loved it. He appreciated the comments. So his video was about something called the quantum, the quantum eraser experiment. Are you familiar with the quantum eraser experiment?
Yeah.
Okay. Have you seen her takedown of that video and showing that it's actually nothing whatsoever?
So do you know what? I haven't seen that video, but I can imagine what she's saying. Because it's a big. So Sabine's take on the quantum eraser, I think, will be that there are certain ways of interpreting this experiment, and it's basically an experiment that says you can alter the behavior of or the character, maybe is a better way of saying, of a particle, of a quantum object. I don't know how to describe these things because they're not waves and they're not particles. So let's call them quantum objects. And you can alter their character by doing something after that character has kind of been formed already. So the quantum eraser seems to suggest that you can kind of have this backwards in time action on stuff. And Sabine's take on that, I think, is that actually there are complexities in how we interpret those experiments that people don't really talk about. So people have generally in quantum physics really just sort of allowed a few different interpretations, but a very few, like 2 or 3, of what's going on in quantum physics to take over. And famously, people say, Schrodinger's cat, it's dead and alive at the same time. So quantum things can be in multiple states at once. And while that's true, in some respects, what it is really saying is we don't really understand exactly how this stuff works. And there's a thing called quantum entanglement where you can talk about it being a weird effect where things affect each other over huge distances instantaneously, where they shouldn't be able to do so because Einstein's relativity tells us that you can't do that.
And spooky action at a distance.
Yeah, exactly. So we're in a position where we sort of just say, okay, that's how it is. And Richard Feynman famously said, don't ask yourself, how can it be like that? It just is like that. And so we sort of accept it. But actually, there are some people, and Sabine's one of them, who are saying, well, there are some hidden assumptions that we need to think about, and need to maybe address, that have kind of just been brushed under the carpet. And I think it's her take on it is a really interesting one. And you have to remember that quantum theory is like 100 years old now. And we're effectively still in pretty much the same philosophical understanding as we were in the 1930s or the 1940s, maybe. In that, people have just said, I believe this. I believe in the multiverse. I believe there's like every time the quantum thing happens, and it sort of happens in a separate universe. And other people will say, no, I believe that actually what's going on is we haven't found the hidden variables that are behind this weird effect. And if we look more closely, we'll find the reason for this. And there's no kind of way to tell between them because we haven't been able to progress the experiments or anything like that. There are reasons to ask difficult questions, which is what Sabina's so good at doing.
She's phenomenal. So yeah, I highly recommend her channel to anybody, as well as Matt Dowd's. His channel is phenomenal as well. His coverage of black holes is unlike anything I've ever seen. So they're all good. And I appreciate that they can critique each other and respond well. So good on them both, I thought.
Yeah, and just talking about the physics thing, like, these unspoken assumptions, right before we get back to the book, I've always found it fascinating that, like, if I take 2 electron beams and, like, let's say I separate them by 1 meter and I fire particles, and that the particles can interact at all. Like, sometimes I wonder, like, where the information of the location comes from. Like, how is the base code of the universe stored? But, like, that just touches other stuff.
I mean,
but
I'll just comment on that. It's a really interesting thing to think about, because we think about, say, separating these things by a meter, and we live in this space and time, in Einstein's sort of space and time, where we have 3 dimensions of space and 1 dimension of time. And it sort of seems to be that's it to us, but actually when you do the maths in physics, say string theory, and trying to work that out, whether you're looking at sort of multiverse or whether you're looking at quantum entanglement, it seems to be that there's something. It's not quite a full explanation to say, there's 3 dimensions of space and 1 of time. So entanglement seems to involve, in some ways, something that acts outside of space and time.
We did an episode on Bell's theorem.
Yeah, so Bell's theorem exactly, sort of depending on certain assumptions that you make, seems to suggest that there's kind of something outside of space and time which allows these kinds of strange correlations to occur. And you can say, it's outside of space and time, or you can say it's just weird. Which is probably what Feynman would have said, is like, stop asking difficult questions. And there's so much left to discover, really, which I find really great. I love the fact that after so many 100 years of doing physics, we just uncovered more and more problems.
Oh yeah, and every time we think it all solved, it seems like somebody discovers something that throws a wrench in the work.
Yeah, exactly.
Like, I know that people thought that physics was solved with the electron formula, and that wasn't.
Well, I mean, at the end of the 19th century, somebody famously said, all the physics is solved now, and there's sort of nothing. There's really nothing to do but fill in a few small gaps. And then along comes Einstein with relativity and quantum theory, and inside about 10 years, that whole thing had been blown apart.
And it seems like almost we're seeing that with dark energy now, is like you mentioned earlier.
Yeah.
Like how it's nobody knows what it is, and it looks like it's not a large scale effect. It looks like it's actually something.
Well, exactly. So we have this anomaly where you've basically got 96% of the universe is in a form that we don't understand. Some of it's dark matter and some of it's dark energy. And there are those who think that it's actually because when we do the equations, and back to maths again, really, when we do the equations and sort of try and work out how to mathematize the universe, maybe we've got some maths missing that we're just not able to do yet, and we need to invent some new mathematics that will allow us to, get much better solutions that make sense of these anomalies that we see in experiments.
And that's actually something that I wanted to touch on, is just, that's what feels, you use the phrase invent new mathematics. And sometimes it still messes with my brain a little bit that you can just do that there are just these things in the world that sometimes are very tangible that we can make new rules to describe, essentially.
Yeah, I mean, I know a lot of mathematicians say it's discovered, not invented. I mean, it becomes a matter of taste, possibly, the way you want to talk about that. But when I look at like Newton and Leibniz with calculus, it really looks to me like they invented it. They didn't discover it, but it seems to me they constructed something that it was an entirely new tool for mathematicians to work with. So it seems to me maths, it just seems to be invented. And I think it's usually invented for strong reasons, like we need this solution to this. So if you're talking about like quadratic equations or quartic equations, the solutions for those had to be kind of discovered. And then the people who were able to do that were then able to kind of use those for banking and finance, and it was basically a new way to make money, to predict how much you could make out of loaning money to a certain rate and things like that. So I think most mathematics seems to come out of really good motivations for, like, I need to do this thing and there isn't a tool available, and it's really rare. I mean, what happened with calculus is extraordinary, and this is an amazingly powerful tool that obviously we're using all the time now. But there was a time when it kind of wasn't there, and somebody had to sort of, I would say, invent it. And others, I guess, would say somebody had to discover these relationships. But for me, I think it's invention.
Right.
And we also get into, sorry, what?
Oh, no, go ahead.
Oh, I was going to say, we also kind of get into semantics there too, because, what is the difference really between an invention and a discovery? I mean, you could say that a discovery is a description of something new. And when you're dealing with something like math, maybe it's like arguing about, like, which side of the coin should fall up, where it's like,
okay. Yeah.
Where it gets to, oh, sorry, continue.
Maybe I shouldn't worry about that. I just worry about offending mathematicians, that's all.
I've noticed that there's a big difference. Physicists tend to say that mathematics is invented, and mathematicians tend to say it's discovered.
Yeah.
Hey, Breaking Math fans. First, I want to thank you for listening. I have an important message for everyone. You can start your own podcast right now with Anchor. Anchor lets you create and distribute your own podcast. Just get an idea, record, and upload. It's just that easy. Anyone can do it. I'm on my way to accomplishing my dream, and you can too. Just get on your device's app store and download Anchor. It contains everything you need to make a podcast. With Anchor, you can put your podcast on all the big platforms: Apple Podcast, Spotify, Google Podcast, Amazon, and more. Reach the whole world with Anchor. Best of all, Anchor is free. You have nothing to lose with a free platform. Download the Anchor app or go to anchor.fm to get started.
I love the relationship historically between mathematicians and physicists.
Oh, I was going to say we did episode 4 on that.
That's right. Yeah. What was it called again?
Language of the universe.
Okay. Yeah, that's right. I recently heard a mathematicians versus physicists joke. I don't know if you guys are familiar with it. Have you guys heard the sheep joke about chemists? Oh, you have? Okay.
No,
okay.
I don't think so.
Oh, very good. Okay. Well, it has something to do with there's a car in, let's say, Scotland, and it's driving through a hilly pasture, and inside the car there is a chemist, a mathematician, and a physicist. As they're driving around the hill, the chemist sees a black sheep and says, "Oh, how about that? In Scotland, there are black sheep." And then the physicist sighs, so annoyed, and said, "Ugh, you biochemist, no. In Scotland, we know that there is at least one black sheep on this hill." And then the mathematician hears that answer and groans and goes, "Ugh, you physicists, no. In Scotland, we know that there is at least one side of one sheep that is black." I thought that's fantastic.
People like that.
Yes. Yeah.
Oh, the whole splitter joiner thing.
Yeah. I love the arrogance and the actually. In fact, there's a show done by a channel called College Humor that has a show called Actually, the show of nerds correcting nerds, and I think that's just a fantastic illustration. You have to chime in by saying actually and then correct whatever the host says. So, I think it's fantastic. So, yeah.
So I got a question. What's your favorite chapter of your book?
I'm gonna say imaginary numbers. I'm kind of, I'm just sort of in awe of these things, and I sort of, I think in some ways they're the whole reason I kind of got started on this, because I just couldn't believe when I was writing the book about Cardano, which is called the Quantum Astrologer's Handbook. It was a few years back. I just sort of started to see the power of imaginary numbers. And when I encountered them at school, I remember being like one of those kids who were like, "Oh, if they're imaginary, why are we bothering learning this kind of stuff? And what use could it possibly be?" and to discover how powerful they are and how they literally, my life wouldn't work without, this conversation couldn't happen without imaginary numbers. I think it's just incredible.
Oh yeah, try designing an antenna with them. Try designing an antenna without them,
On this podcast, we like square roots of -1.
We're also like solutions to quadratics that use quaternions. And I know that octonions, actually, we did an episode where we talked about how they're essential to the structure of a kind of cosmology.
I think I mentioned in the book that there's a Roger Penrose quote where he's like, clearly nature requires us to use complex numbers to describe it. It's like has to be there. And then you've got, the quaternions and the octonions seem to be the kind of the way in which that happens. And people trying to construct quantum gravity theories that unite quantum physics with relativity, they're using octonions. And I love that. The fact that, that William Hamilton was like, oh, I wonder if there are any more imaginary numbers, and then comes up eventually with the quaternions. And then his friend, like 2 weeks later or something, comes up with the octonions. And they were like, oh, I wonder if there's any more. And it turns out you literally can't make any more. I mean, it's been proved that those are the full sets of numbers. And
aren't there 16 entry ones, but that aren't commutative or like almost anything? Like there's just very rudimentary operations that can be done.
I
in
think
them?
they behave in a very different and non-helpful way, if that's the case.
Gotcha.
I'm not entirely sure. But then, so then I discovered that this whole quaternion thing was like behind, the Mad Hatter's Tea Party in Alice in Wonderland, and Charles Dodgson, who wrote that book, hated them and thought that we should only be teaching stuff that's in Euclid, and it had just been brought into the Oxford curriculum, the syllabus for the students there, and he was a teacher there and was trying to get the dean of the college to stop people teaching quaternions. And the dean of the college's daughter was Alice, and the Alice of Alice in Wonderland. And so he kind of wrote this book. He'd been writing this book anyway, and then put in this absurd sort of scene about things, rotating around certain ways and time being missing, and it's always 6 o'clock, and it's just like, when you delve into it, and there's scholars who've delved into this, you find that, this is kind of Charles Dodgson's way of protesting about this new mathematics. And, you read this story and you never know. I mean, I only come across that when I was writing the book. I didn't realize that this was in there. But it's literally, these things are so sort of revolutionary and so different to everything in traditional mathematics that this literary protest is going on, right under our noses. And, so he would have given the dean of the college this book because it was, about his daughter, a book featuring his daughter, Alice. And the scholar that I spoke to about this said, it was almost certainly like some kind of, throwing shade, to know that, he'd used his daughter as a character in this book that was actually, having a dig at his mathematics syllabus as well. So, I just love the subtle complexity of that.
Oh, yeah, definitely.
You'd mentioned one thing about one of the, I think when we asked you what was the hardest chapter, you talked about Shannon's information theory chapter. That's the first chapter I dove into because I'm a little bit obsessed with Shannon's information theory. You had mentioned something that made me a little bit crestfallen in that chapter. You talked about that after Shannon published his work, there were a lot of people who tried very hard to apply Shannon's information theory to other fields, including things like biology. Ever since I read Gödel, Escher, Bach, and his explanations of how to explain perhaps where consciousness comes from with processes, inside the brain, I've tried to apply Shannon's information theory to that. And then reading that Claude Shannon actively discouraged people from going to, I was like, really? Oh, man.
I think what's interesting about that is I think immediately everyone saw that this was a kind of revolutionary way of looking at something. And of course, so much of what we deal with in science is information, right? You get sort of these inputs and outputs in terms of, even in terms of experiments. You do something, you get an output, and you kind of make inference about it. And I think what Shannon found was that straight away, everyone was trying to kind of find ways to mathematize literally everything, using his information theory. And so I think his sort of view was, whoa, it's literally to, sort of, help us to encode, signals and that kind of thing, not necessarily, to do all this other stuff. But at the same time, of course, consciousness researchers are aware that there is, these signals in our brains. There is a passage of information around the cortex there's clearly something going on that's akin to sending a signal down a wire. And so, of course, consciousness researchers are going to want to use information theory. And the leading theory of consciousness at the moment is integrated information theory, which is IIT, by Giulio Tononi's ideas. Despite Shannon's kind of reticence for people to do this, I think people have just plowed on anyway. And I think they're probably right to, because I think it's a very profound and far-reaching theory, and probably more far-reaching than Shannon even himself appreciated.
Sorry, I was going to ask you, the name of, you had said somebody is the leading researcher in consciousness. Will you say that name one more time? Maybe we can put it in our notes.
So what I said was, this guy called Giulio Tononi came up with an idea called integrated information theory, which is kind of the leading theory behind consciousness. So there's a few theoretical approaches to explaining consciousness, none of which, I should say, really are fully doing the job yet. But it's kind of the most accepted and probably the most worked on one.
I was also struck by, like you were saying, people interact with information theory all the time, and it's not really understood or taught in schools, which I think is fascinating because it really isn't that much harder to understand than logarithms, which, like, if you understand multiplication and addition, you understand logarithms. If you're taught properly. I mean, we use the word byte like constantly. I mean, nobody uses Nat or Shannon anymore, but
yeah,
not that I know of.
I mean, I guess you would ask the question of do school students need to learn information theory? And I guess they probably don't. These things take time to hit the syllabus and hit the curriculum, don't they? And information theory is quite possibly the kind of newest innovation in some ways. And I would imagine that educators are just, not yet ready to include it. I mean, you learn it when you get to university if you're doing that technical discipline that requires it. And it's probably a lot to put on. I mean, already, I know in the US, students learn calculus, and that's kind of the pinnacle, and that's, quite off-putting for a lot of people already. So, maybe information theory would be a step too far.
Oh yeah, I wish that. I mean, you talk about the American education system, which is broken in so many ways. But one thing that really struck me about information theory, just learning it, was how often it could be applied. Like, I think about it constantly now. Like, sometimes I think about the amount of what is it? The thing that you send a bit of information into a black hole and it increases by 1 square Planck area. There's just something obviously so fundamental to it that I wish that we had more time for exploratory courses, things like that. I honestly think that the first 5 or 6 years of math education should just be concepts and stories. Like, I don't think people should even touch. If you're not the type of age, I think, where you'd balance a checkbook, I don't think that you should really bother learning quadratic equations yet.
Well, that's a really interesting perspective. I mean, I think the educator's perspective would be you need to test them at the end of the year, and you can't test them on stories.
Oh yeah, but you totally could. You could have them write comprehensive essays and then grade them on that. Plus, you would have people really thinking about math as a real thing, the real thing that it is, rather than this thing I have to do for an hour a day that I hate.
Yeah, I completely agree with you, and I think actually, when people learn, particularly the stories behind math, I think, you can apply them in interesting ways, and it might take you into other disciplines, and you can imagine just people sort of, rather than learning or rather not learning the math because they just can't sort of get their heads around it and they don't want to learn it, and they sort of get this mental block. And, we haven't talked about math anxiety, which is a huge problem in the classroom. If you had people sort of talking about how math was progressed and what it was used for, then I think you give people tools to apply in other areas of their life. And they might not go into technical disciplines, but they might sort of still use that appreciation of the human story to kind of applying in other areas.
Yeah, because it strikes me that we teach language in a way that appeals to everyone, science in a way that appeals to more people, but it seems like we teach mathematics in a way that seems to be only aimed at people who are profoundly mathematically minded, for them to get any enjoyment.
Yeah, I completely agree with that. And I think there is an issue over how much math you need to learn to be able to negotiate things in life, like, shopping, understanding, discounted things in supermarkets, balancing your checkbook, as you say, knowing what a 4% pay rise means, if you're in the workplace, is and those are kind of really important aspects of maths. And then people who are going to go on to technical careers, obviously, and love it and find it easy to do, then they're going to just like progress anyway. There are certainly people here in the UK who are suggesting that there should be a kind of qualification of numeracy, maths for living, rather than just like passing an exam at 16 and that being the kind of pass or fail.
There's a whole chapter in Richard Feynman's book, Surely You Must Be Joking, Mr. Feynman, where he talks about conversations between himself as a physicist and one of his eclectic artistic friends, and they made attempts to teach each other's worlds. And I think in the chapter, the artistic guy does a lot better job getting Feynman to appreciate art than Feynman does getting the artistic guy to appreciate anything with physics, which I found disappointing because I consider myself to be an artist who loves physics. But I love the conversation about there's a term in here in America. I don't know how ubiquitous this term is, but this phrase where they talk about explaining physics for poets, but also you could have poetry for physicists. You know what I mean? And just like try to meet in the middle there. So which I think this book, your book does a great job with, and other things as well.
Oh yeah, and I just to tack on to that, the chapter on logarithms, I feel like if I hadn't understood logarithms before going in, I would have a much better chance of learning all the formulas after reading that chapter, and which is kind of the same goal that we have with our podcast. The episodes we try to kind of be like Nova for math, but
it's the logarithms is an interesting thing because that chapter, in some ways, you don't need to do logarithms today. It's all in the calculator. So you punch a button on the calculator, and you kind of have that thing there. And you almost don't need to know what that is. You just need to know that is the button you need to push. But for me, I think that it was so fundamental and so transformative when it was invented, and it was originally invented to make astronomers' lives easier, and then it started making sailors' lives easier as they did their celestial calculations. And then you find that actually, all of science is kind of built on it. And Newton, so from the logarithm you get the slide rule, and then Newton invented his own slide rule, and Stephenson invented a slide rule to power the Industrial Revolution in Britain. And Enrico Fermi always carried a slide rule when he was doing his atomic bomb calculations. And you would think, this little thing, the logarithm, was at the center of so many kind of world events, historical events of huge significance. And I think that's why you need to learn about logarithms. Not you can just push the button on the calculator if you like, but I think you get a much sort of broader perspective on humanity if you understand that this kind of innovation, doing this kind of work to create logarithms, actually changed the world over the next sort of 200 years.
That's the thing that I think with the technology we have nowadays, I think it's much more useful to know how to operate a calculator. I used to tutor math quite often, and I tutored someone who knew how to do write out multiplication and all this stuff, could do all the little algorithms, but didn't understand on a fundamental level what multiplication was.
Yeah.
I had to use Pebbles to teach this 20-something-year-old person with an incredible amount of math anxiety, a completely unfair amount that I hate seeing. It disgusts me to see, honestly, so many people with math anxiety, because it makes me realize that they are taught math abusively, to put it bluntly.
Yeah, that's an interesting word to use, actually, because I was having a conversation with a friend last night who said exactly that. We were talking about something, and they were talking about their experience of learning math in school, and it wasn't just math; it was some other things. But they said it was an abuse. If I got a question wrong, I would get shouted at, and I would get belittled, and it didn't help me to learn. It just taught me to keep my mouth shut. And I think with math anxiety, which is a huge problem. I saw a statistic that was something like 93% of adults in the US feel some sort of sense of alarm if they're presented with something mathematical to do. So we're scarring people at school, it seems to me. And there must be a better way somehow. There must be, and I'm not saying this is all math teachers at all, and I'm not even blaming math teachers.
Oh, no.
Because I think they have to teach people to get through to jump the hoops that have to be jumped, to make progress through the system. But I think there must be some kind of way in which we can make math less scary. And I think these stories, and I think the kind of understanding that math doesn't come naturally to us as human beings actually would help. So, I start the whole book by saying, look, our brains didn't evolve to deal with numbers. None of the animals deal with numbers in the same way that we do. We just happen to have come across a way to sort of adapt some of the circuits in our brain that are normally, keeping track of our fingers, and we use them to keep track of numbers. And suddenly, we've got this incredibly powerful tool that we've just built on, and we transmit it culturally. So nobody's born learning. Nobody's born knowing how to do math, but we very early in their lives we teach them how to do the basics because it's so incredibly useful. And there are cultures that don't do math and don't count beyond 3. In the Amazon, for instance, there's the Piraha tribe who literally just say, they'll count to 3. This is where the title of the book comes from, and then they'll say more. So, and that more is kind of everything that we celebrate as math. I think it would be really important for students at school to start off by learning that this is hard. This isn't a natural thing. You shouldn't just be able to do it. You're going to have to sort of think a little bit, and you're maybe going to have to struggle a little bit, but it's worth it. And be a bit more gracious and forgiving towards people who struggle with math.
Oh yeah, absolutely. The same way we are with language. I mean, a lot of times people who have trouble with language, like we shouted at it about language for it, like, and that's the thing. Even with mathematics, I've heard people talk about even their parents. A lot of people here in the United States, I've heard this story from helping them with their math homework at the kitchen table or whatever, and then just like berating them when they get answers wrong. Yeah. Which like it's just like you get it from both ends. You get it from school and you get it from home with some people. Which it just, I mean, I guess there's bigger questions to be asked as well, such as what is the culture that does this? Why does it do that? But I guess you get into all this question with math.
The alarming thing for me is that if you have children after you are math anxious, so anyone who leaves school with math anxiety goes on to have a family, if they help those children with the homework, and this has been shown in numerous studies, you help those children with their math homework, and you actually pass on the anxiety. It sort of cascades down the generations. And it's the same if you have math teachers who aren't 100% confident and have a little bit of anxiety. The students will sense this and they pick up on it and they become anxious themselves. And there's study after study that shows that, if we don't fix this problem, it's never going to go away, right? Because it is being passed on.
Oh yeah, which one trick that I would sometimes use with math students is just because I realized it was an issue of them feeling like they didn't have like enough like mental processing power in some cases. I would just teach them like some mnemonics tricks having nothing to do with math. I would teach them how to remember like 15 numbers in a row or something like that, and then they'd be like, "Wow, I could do that!" And it's like you could totally do that. You could do math too.
Yeah.
You listen to Breaking Math, which probably means you're a big nerd. And you're in good company. We're all big nerds here at Breaking Math, and I want to talk to you about Brilliant. Brilliant is a one-stop shop for math and science. They have everything from lectures on number theory to mind-expanding puzzles and exercises. And how do you learn this, you might ask? Through both presented information and problems to solve. After all, you learn best by actively using your knowledge. This week, we want to feature a wonderful course on machine learning. It is one of many courses in data science available on Brilliant. So what are you waiting for? Sign up at brilliant.org/breakingmath. The first 250 listeners get 20% off the annual subscription. That's brilliant.org/breakingmath. Any last remarks, Michael?
I guess the thing I would really like people to take away from this book is a sense of wonder, kind of as I was saying about the fact that we are the only species of animal on the planet that does math like this, that deals with numbers, and and our brains aren't that different to the great apes. They're not like, it's not like orders of magnitude difference, and yet we do this thing which just elevates us so much, and all of our elevation, this is my whole argument, comes from this ability to kind of just start to deal with numbers. And I just think it's an extraordinary thing, that we take it for granted, really, that the ability to just count and then group numbers and then see shapes and measure shapes. And this is powerful stuff.
Oh yeah, it's wonderful brain program?
I'm working with a lot of local educators, actually, who are interested in podcasting, and I'm actually going to reach out to a lot of math teachers. I bet a lot of them would love your book, especially for giving a little more historical context, and the book perhaps would be recommended, if not for the students, if they're too young, then perhaps for the parents, for sure, especially those, Yeah. So I'll definitely be plugging your book to that population, as well as obviously to our Breaking Math listeners. Our Breaking Math listeners who would like to hear more about you and your ideas, do you have a Twitter or a social media presence?
Yeah, so I'm Dr. Michael Brooks on Twitter.
Okay. All right. Oh, there you are. Oh, cool. I like your profile picture. I like it. Your hands are up like this, like you're giving somebody.
I think I'm talking. Yeah. I can't keep my hands still when I talk.
Oh, yeah. Same here.
What's the book and where can people get it?
So the book is The Art of More, How Mathematics Created Civilization. It's in all good bookshops. It's on Amazon. It's anywhere you would normally source a book, I would say, you'll find it.
Well, Michael, thank you so much for being on the show. Your book is The Art of More, and it can be found wherever books can be found. And you are Dr. Michael Brooks on Twitter.
Yeah. Thank you for having me.
Absolutely. Merle, any last closing remarks before we close it?
I just want to say I had a lot of fun, and I am glad that I picked your favorite chapter to talk about.
That
was awesome. Yeah. All right. Again, thank you, sir. We greatly appreciate that. And with that, I'll go ahead and stop.